All right, 12.1, explore solids. This is just an introduction to three-dimensional solids. Go ahead and draw this trapezoidal prism in your notes. If you need to pause the video, go ahead and do that. Just want to identify the different pieces of a polygon, or excuse me, a polyhedron. We have our vertex, which is the point at which two edges meet. Our edge is one of the straight sides like this, and our face is one of the two-dimensional closed areas, polygons. So go ahead and draw this down and go ahead and label faces, edges, and vertex and identify what they are from this, these words here. All right, go ahead and draw the difference between a polyhedra and a not polyhedra examples. Polyhedrons have straight edges like prisms and pyramids, whereas the curved edges like spheres, cones, and cylinders are not considered polyhedra. Just a terminology, get that down. All right, difference between a pyramid and a prism. A pyramid has one base and a point that those bases have faces that meet at. And then a prism has two bases. In this case, the bases are pentagons, right here and right here. But the faces connecting the two bases are rectangles, always rectangles, to make it a prism. The bases can be anything. Now this is mostly a review from middle school, so that's why I'm zipping through this. But go ahead and draw an example of the prism and an example of a pyramid in your notes, please. All right, it says tell whether the solid is a polyhedron, and then if it is, name the polyhedron and find the number of faces, vertices, and edges. So I'm going to go ahead and establish on letter A, we have two bases. Now, since it's a rectangular prism, it really doesn't matter what you call the base, because it could just be the bottom or it could be the face, could be the bottom for one of the bases, but it really doesn't matter because when finding areas and such, it'll be the same thing. So this is a rectangular prism. The edges, and let's do the faces first. I've just memorized that prisms have 6, rectangular prisms do, but we have the front face, the back face, and then we have 4 going around the prism itself. That means the faces there are 6 faces. Then we're looking for the edges. Notice there are 4 on this base, 4 on this base, and then 4 going around. That means there are, and this is the edges, there are 4 plus 4 plus 4, which is 12. And then we have the last thing, which is the vertices. There are 4 here on the front, and there are 4 on the back. So the vertices is 4. Go ahead and try the next two, letter B and letter C, and then I want you to look it up in your textbook because I want you guys to get more familiar with using your textbook and finding the answers for B and for C. All right, tell whether the solid is the polyhedron. If it is, name the polyhedron and find the number of faces, vertices, and edges. Pause the video, try these 3 problems, see if you get the same thing as. All right, this is what I got. We have a yes, no, and yes as regards to being polyhedra. This has a curved face, which means it's not a polyhedron. And then this is a square pyramid because it meets at a point. In fact, I don't think I can say square for sure, but I can definitely say rectangular pyramid. It looks like a, oh wait, I'm sorry. It has the 4 marks, which means it is definitely a square. Apologize. All right, and then we're looking for the faces, vertices, and the edges. There are 4 faces, 4 going around, 1 on the bottom. Then we have vertices, 1, 2, 3, 4, plus the 1 on top. Then we have the edges, 1, 2, 3, 4, 5, 6, 7, 8. Easy stuff. And the same thing over here. The trick with this one, though, is noticing that, yes, there is a triangle, but there is a triangle, 2 triangles connected by rectangles. If they're connected by rectangles, then it's a prism. This is Euler's theorem. It's just relating the faces, the vertices, and the edges. I'm not going to ask you to memorize this. I will give it to you on any quiz or test. And if you have the formula, it's just merely plug and chug the input values and getting out an output value. So we have F plus V is equal to E plus 2. Go ahead and write this in your notes and draw that right there connected with these numbers. All right, I'm just going to talk through this one without actually writing anything. It says find the number of the edges on the frame of the house. Now it's not talking about all the little boards right here. It's talking about the actual edges like this. So you just need to count it up, apply Euler's theorem, and once you start getting some of the values and then finding an unknown value. Okay, go ahead and draw a regular convex and a non-regular concave. you can think of a concave as caving in. Or if you were to draw a diagonal between non-adjacent vertices of the polyhedron, then you would find that the diagonal can be outside. If there's at least one outside, then it's concave because it caves in. This is convex. Draw both of these in your notes. Write the words convex and concave. All right, Platonic solids. I'm just going to talk about it here, but this is not really a huge deal with what we do here in the state of Texas. So we have regular tetrahedron. That's 4 faces triangular. By the way, if it's regular, that means all of the faces are congruent. We have a cube. You're familiar with that one. Octahedron has the 8 faces that are all congruent. And then we have a dodecahedron. This is 5-sided figure, 12 faces to make this figure. And then we have an icosahedron, which is 20 faces of equilateral triangles. We don't work with this a whole lot because they're pretty difficult to do volumes and some other things with them. So it's really just getting familiar with the word Platonic solids because of a guy named Plato. Using Euler's theorem. In this case, all you need to do is find the number of faces, vertices, and edges, and then check it with the Euler's theorem. So go ahead and count them out. In fact, I'm going to pause the video and do this. So this is what I counted from the diagram. Then I used Euler's theorem to check it out, and boom, it does check out. All right, a cross-section. A cross-section is a 2-dimensional cut on a 3-dimensional object. Let's say we take this plane right here, and we chop through this 3-dimensional object. When you do that, you get this cross-section area. Sorry about the bell. In this case, it's a triangle. So the cross-section is the part that's cut off, a 2-dimensional part that's cut off from a 3-dimensional figure. Go ahead and identify this, draw this, and write what I said on there, please. All right, now we just have to identify the cross-section that's formed by the plane and the cube. Notice in this case, we have, if this plane is parallel to these faces, which we'll assume that it is, then this also is a square that's intersected by the plane and the cube. In this case, we know that this segment is longer than this segment because this segment is the same as this one, and this one is √2 times it. So this one has to be a rectangle, not necessarily a square. In fact, it's not a square. In this case, we have these 2 lines parallel because in a cube, the faces on the top and the bottom are parallel. Top and the bottom are parallel, so those lines are parallel. And these, since this plane is slanted, are not parallel. So this is a trapezoid. We don't know if this distance is equal to this distance, so we can't say that this distance is equal to that one. So the only thing we can say for sure is that it's a trapezoid. All right, go ahead and pause the video and see if you get the same thing as me on these. I decided not to do number 4 because it's pretty repetitive from what we did before. But we do see that this one's a triangle, and this one's a circle. If this were slanted, then it would just be an ellipse or oval. And here we have a hexagon that's cut off by the cross-section. That's it for these notes.